Traditionally, imaging systems were designed to capture data for human eyes. But modern imaging systems capture data for computers. Algorithms don't need human interpretable images, which allows data to be captured in new ways. This raises questions like, what are the best filters for color photography? Where should radio telescopes be placed on Earth to image a black hole? Can conventional lenses be replaced by non-traditional optics? And how should microscope illumination be designed to reveal cellular phenotypes? To answer questions like these, we developed a technique that can evaluate and design imaging systems using information theory. Many existing evaluation methods decode measurements to assess performance on downstream tasks. In contrast, our approach avoids this complexity by directly quantifying information in raw measurements. Our approach can be applied to diverse imaging systems and in real-world conditions where the objects being imaged may be unknown. It also enables efficient, automated design of imaging systems in simulation. Here's a concrete example. Cameras use filters to capture different colors at different pixel locations. The conventional design is the Bayer pattern shown here. However, many alternative designs are also possible. Since each pixel measures only one color, raw measurements must be processed to reconstruct full color images. The filter can then be evaluated by comparing these reconstructions to a known ground truth. Our information estimation approach, however, eliminates the need for both reconstruction and ground truth. Instead, our technique uses a dataset of raw measurements from different objects. It then estimates the information content of each set of measurements to quantify the performance of different filters. In our experiments, measurements with higher information estimates, such as the blue point, consistently produced better reconstructions. This validates that information estimates alone can assess imaging system designs. The same relationship held across all 4 domains we tested. Beyond evaluation, information estimates can guide the automated design of imaging systems in simulation. Using a mathematical model of the imaging system, we can use gradient-based optimization to iteratively improve designs based on how much information they capture. The resulting designs achieve better reconstructions despite never optimizing for reconstruction quality. A key property of information is that it synthesizes all factors that determine how well objects can be distinguished using measurements. For example, consider taking pictures of trees. Different trees are easily identified from clean measurements, which contain abundant information. However, when noise increases, different trees could have produced the same measurement, which means the measurements contain less information. Similarly, a loss of resolution can decrease information, as can a loss of color. Information combines the effects of all of these factors. Here's how our estimator works. Information depends on diversity. More diverse signals can carry more information about the object. However, the diversity of measurements can come from either the object or from noise. So our approach first estimates the total diversity in the measurements, and then subtracts away the diversity from noise alone. Mathematically, this can be represented as a difference of 2 entropies. These entropies can be written as expected values, which depend on 2 key probability distributions: the distribution of measurements, P of y, and the distribution of measurements given clean images, P of y given x. Though P of y is unknown, a dataset of noisy measurements can be used to estimate it by fitting a model, P theta. The distribution of measurements given clean images describes the noise process. For example, for a particular clean image, samples from this distribution represent its different possible noisy measurements. By estimating both distributions, our method quantifies information, which determines how well objects can be distinguished using measurements. For a given measurement dataset, better models more accurately concentrate probability mass on the underlying true distribution. This will produce more accurate information estimates. To see why, consider the entropy term being estimated. This entropy depends on the true distribution, P of y. Since this distribution is unknown, we estimate it with our model, P theta of y. This forms an upper bound on the true entropy. By fitting better models, the estimate of entropy becomes increasingly close to its true value. We developed several models for our estimator. One was based on a Gaussian process. It is fast and requires less data, but is less accurate. Another was based on a pixel CNN neural network. It requires more resources, but produces more accurate estimates. In summary, our work enables practical information-based evaluation and design of imaging systems across many domains. To learn more and try our methods yourself, visit the project website shown here.